Hello students, we will discuss module 3. In module 3, Maxwell's equations, electromagnetic waves and optical fibers are the three chapters. In that, first we start with optical fibers chapter. Earlier, for the communication purpose, copper wires are used through which the electrons were sent. In that way, the telecommunication was worked. Later, with the help of microwaves, the microwaves are sent in the space. From there, the antenna is tapped with the help of mobile or the other receiving media. Like this, the microwave communication was established. But now, based on the demand which is there for the communication, after the invention of lasers in 1960, the communication system changed from microwaves to the optical fiber communication. In the optical fiber communication, optical fibers are treated as the guiding channel through which the optical frequency of about 10 to the power of 15 hertz we can send, which is 1000 times more information can be sent compared to the microwave systems. So that means optical fiber communication is 1000 times more powerful, more capacity than the microwave communication. Energy of light waves gets dissipated in open atmosphere easily. Hence, there is a need of guiding channel for optical signals, just like the metal wires are used to guide the electrical currents. Okay, so for that purpose, the optical fibers were used. Optical fiber is very thin glass or plastic designed material of a size of a few micrometer, which is used to guide light waves along the length of the fiber. These fibers send the information from one end to the other end based on large number of successive total internal reflections. Much of the light launched into one end will emerge from the other end with a small losses. Fiber optics is a technology that uses these optical fibers to transmit data from one end to the other end. The fiber optic cable consists of bundle of glass fibers, that is optical fibers, which are protected by a PVC jacket. Optical fibers has many number of advantages over the copper wire or over the microwaves. First one is lightweight. The fibers are lightweight. Transportation will be easy. No tapping, no crosstalks, and one more important thing is which is protected by electromagnetic interference effect. It can carry more data as their bandwidth is very large and information is in the digital form. Here electromagnetic interference, generally it is called as EMI. So electromagnetic interference means the interference of one signal with the other signal. Like if you keep the mobile phone near to a television or near to your computer system, if a call comes to your mobile phone, it distorts the display in the TV or the computer, or it may distort the sound waves. That it is called as EMI effect. That EMI effect will not be there when you use the optical fibers. And then the losses in the fiber is also minimum, very less compared to the other communication systems. And one more important thing, because of these optical fibers which are laid from one end to the other end beneath the sea, from one continent to the other continent, we are able to enjoy the internet facility, that is the broadband internet facility, where you can tap the data, you can send the data in the form of audio, video or any other forms from one system to the other system, which is because of these optical fibers. The next slide will tell you the blow up of the syllabus for in this chapter. In the blow up of the syllabus, you can see a description of propagation mechanism of light through an optical fiber. That means here we discuss the physics behind the propagation of light through the optical fibers, where the condition it comes, that is the acceptance angle and the numerical aperture. We derive the expression for numerical aperture and acceptance angle, and we discuss the conditions for the successive total internal reflection, so that the light always propagates through the core region of the optical fiber. The numericals on these expressions is also important, and along with that, qualitatively we discuss about the V number or V parameter, and then the number of modes the given fiber supports. Also, we discuss the different types of optical fibers based on the material what we use, based on the number of modes the fiber supports, and based on the refractive index profile, how it is designed for that particular fiber. Next, we discuss about the losses in the optical fibers. When you see the losses, there are two kinds of losses in optical fibers. One is the attenuation loss and the other one is the dispersion loss. In the attenuation loss, when the signal propagates through the fiber, the amplitude of the signal decreases. That is called attenuation loss. The other one is dispersion loss, where when the wave propagates through the fiber, the signal when it propagates through the fiber, the full width of maxima of a signal broadens. That is considered as dispersion loss. But in your syllabus, only the attenuation loss is there. We have to write the expression for the attenuation loss. No need of derivation. Definition, expression for attenuation loss, and the causes for this attenuation loss. Okay, so these things we will discuss it in the particular topic. At the end, we conclude this particular chapter with the applications of optical fibers. In those applications, we mainly discuss on point-to-point communication. That is, in the optical telecommunication, how from one point, that is from the transmission side to the receiving side, how the total process it happens. With the help of a block diagram, we discuss it in brief. And this chapter concludes with the merits and demerits of optical fiber communication. Numericals on the first topic, that is the angle of acceptance and numerical aperture. Next, the numericals on number of modes and V parameter. Next, the numericals on attenuation coefficient. These three are important. So in the tutorial class, numericals you must solve many number of numericals by taking different books, where the exercise problems if you solve, then it will boost up your confidence level. To understand the phenomena associated with the optical fiber through which the light propagation, you must know the reflection, refraction, and one more important phenomena, that is total internal reflection. Reflection means when the light propagates from one medium to the next medium at the interface. See here you have one diagram. In this diagram, x dash is the line which separates one medium with the other medium. Let us consider n1 is the refractive index of the first medium, n2 is the refractive index of the second medium. When light propagates from the first medium to the second medium, if it reflects back completely to the first medium, then it is called as reflection. There are two laws associated with the reflection, that is the incident ray, reflected ray, and the normal drawn at the point of incidence. All the three lies in the same plane. The second one is angle of incidence is equal to the angle of reflection. Similarly, for refraction also you have the incident ray, the refracted ray, and the normal drawn at the point of incidence, they all lie in the same plane. This is same as the earlier one. The second one, that is Snell's law, we call it as. According to the Snell's law, the ratio of the refractive indices is equal to the ratios of sine of the angle of incidence to the sine of the angle of refraction. In the case of refraction, the light propagates through the second medium, and the speed of the light also changes when it propagates from the first medium to the second medium. If the first medium is rarer and the second medium is denser, then the velocity of the light decreases. Because of decrease in the velocity of light, the light bends towards the normal. The other case, when the light travels from denser medium to the rarer medium, that is what this diagram says here. N1 is greater than N2. That means the light ray here, it is AO, the light ray if you take, it is going from denser medium to the rarer medium. Hence, the velocity of light in the rarer medium increases, hence it bends away from the normal. That means here, in this case, theta 1 is lesser than theta 2, or theta 2 is greater than theta 1. Fine. So now there comes a special case, like if you see this diagram, you can go on observe the angle of incidence keeps on change when it propagates through the fiber in the core region. For a particular angle of incidence, there is a just grazing of the light ray at the core cladding interface. If the angle of incidence is more than that here, then there is a total internal reflection inside the core cladding, that is inside the core region. That means you have a particular condition here for the light wave to propagate. That condition we will derive it in the next successive slides. In this particular slide, we will discuss about the total internal reflection. So there are two conditions for total internal reflection. The first condition is light must travel from denser medium to rarer medium. Here denser and rarer, it is based on the optical one, that is optically denser means whose refractive index should be more than the second one, the another medium. Okay, so when the refractive index is more, we call it as denser, compared to the other one whose refractive index is less, which is called as rarer medium. It is a relative term. The second condition is angle of incidence must be greater than the critical angle. If the angle of incidence is less than the critical angle, then the light undergoes normal refraction phenomena. If the angle of incidence is equal to critical angle, then light ray grazes the surface which separates the two media. So for us, we require a total internal reflection completely. For this one, the angle of incidence must be greater than the critical angle. Here you can see how to get the expression for the critical angle. In the right hand side of this slide, you apply Snell's law. So when you apply Snell's law, it is easy to write instead of taking the ratios of refractive indices, comparing that with the ratios of the sine of the angle of incidence to the sine of angle of refraction. You just cross multiply, you get the product of refractive index with the sine of the angle of incidence, which is equal to refractive index into the sine of the angle of refraction. Here refractive indices are in the same medium, right? So that means sine theta 1 is in the first medium, then you multiply the refractive index of that first medium. That is equal to the refractive index of the second medium into sine of the angle in the second medium. That is theta 2 is the angle of refraction. Okay, theta 1 is the angle of incidence. For total internal reflection to happen, theta 1 must be greater than theta c. Here, for getting the expression for critical angle, you can take theta 1 as equal to theta c. Then the light ray just grazes the surface. That means the angle of refraction becomes 90 degree. Hence sine of 90 becomes 1. You get this expression as n1 equal to sine theta c, which is equal to n2, or theta c is equal to sine inverse of n2 by n1. By sending n1 to the right hand side, then you send sine to the other side, then it becomes sine inverse. So in that way, the expression for critical angle is theta c is equal to sine inverse of n2 by n1. So for total internal reflection to occur, the angle of incidence should be greater than theta c. Then only the entire energy is returned back and it will propagate through the core region. And it should not happen one time. Successively this should repeat. For the successive total internal reflection, what are the conditions, how the core size and cladding size should be, all those things we will discuss it in the next slides. As it is told in the first slide, optical fibers, they are very thin. They are made up of transparent dielectric materials which are cylindrical in shape, coaxial cylinders. Inner cylindrical part is called as core, whose refractive index take it as n1. The outer part next to that, it is called as cladding. Let us take its refractive index as n2, which is further covered with the polyurethane jacket. That polyurethane jacket is for providing the mechanical strength to the fiber, because dielectric materials are brittle in nature. Hence you require a mechanical support to that. Such type of many fibers are grouped to make a cable. Okay, so here you should know the refractive index of core is greater than the refractive index of cladding. That means n1 is greater than n2. And the diagram here, it shows that once the light enters into the fiber, it undergoes total internal reflection many times, even though the fiber is straight or it is bent within some limited values. Okay, so you can't bend the fibers to a larger extent. There will be a bending limit. Within that bending limit, the light undergo successive total internal reflection. Sharp bends leads to a more loss in the fiber. Angle of acceptance and numerical aperture. This is what the relations we are going to derive in this particular derivation. For this, let us consider a cross-sectional view of an optical fiber as shown in this diagram. The light undergoes total internal reflection, that you can see it in this animated diagram. So you can see that the light propagates only through the core region. Any light entering into the cladding is considered as a loss. Okay, so consider a light ray AO which incident at point O from A, that means from the surrounding medium. Let us consider the surrounding medium refractive index as n0. From this, the light ray enters into the core region at point O. So the dotted line here, it indicates the axis of the fiber. Since it is incidenting with an angle of theta naught and it is going from the rarer medium to denser medium, because the surrounding medium may be a air medium or water medium whose refractive index is less than the refractive index of core. So that is, the core refractive index is n1. Since the light ray is going from rarer medium to denser medium, it bends towards the normal. So here theta 1 is the angle of refraction at point O. Now this light ray O, it incidents at B. OB, the light ray, it incidents at the core cladding interface, that is at point B. Here the angle of incidence will be 90 minus theta 1. How it is 90 minus theta 1? If we extend this vertical dotted line to meet the axis of the fiber, then you have a right angle triangle here OB and the point here where it meets this, right? So the angle is 90 degree. So the sum of the angles of a triangle is equal to 180 degree. So here it is 90 degree and this side it is theta 1. hence the angle OB and this point, it will be theta 90 minus theta 1. So if the angle of incidence is 90 minus theta 1, let us consider this angle is equal to critical angle, that is 90 minus theta 1 is the critical angle. Then the light ray BC just grazes the surface which separates the core and cladding interface. So the angle of refraction here, it becomes 90 degree, and the angle of incidence here, it becomes the critical angle, and that critical angle is equal to 90 minus theta 1. Let us apply the Snell's law at 2 points. The first point is at O and the second point is at B. When you apply Snell's law at O, it is n naught into sine of theta naught, that is the refractive index and the sine of the angle of incidence, which is equal to n1, that is refractive index of core, into sine of an angle of refraction here, that is theta 1. So you have n naught sine theta 1 sine theta naught, which is equal to n1 sine theta 1. Okay, so from Snell's law at point O, you can write n naught sine theta naught, which is equal to n1 sine theta 1. Call this as equation number 1. Similarly, at point B, the angle of incidence is 90 minus theta 1. For this, if you apply the Snell's law, the refractive index of core, that is n1, into sine of an angle of incidence, that is sine of 90 minus theta 1, which is equal to n2, that is the refractive index of cladding, into sine of 90 degree, that is the angle of refraction in the cladding region is 90 degree. Hence you get n1 cos theta 1 equal to n2. So when you rearrange this equation, then it becomes cos theta 1 equal to n2 by n1. Call this as equation number 2. So from equation 1, you can rearrange that equation as sin theta naught equal to n1 by n0 into sin theta 1. From equation 2, cos theta 1 can be written as, sin theta 1 can be written as under root 1 minus cos square theta 1, that is using trigonometric identity, that is sin square theta plus cos square theta equal to 1. You can rearrange for sin theta equal to, so sin theta, it becomes sin theta equal to under root 1 minus cos square theta. The same concept it is used here. So in the place of sin theta 1, you can write under root of 1 minus cos square theta 1. From equation 2, you can substitute the value of cos theta 1, then it becomes under root 1 minus n2 square by n1 square. n1 by n0 is outside the square root. Within the square root, you have under root 1 minus n2 square by n1 square. If you take the LCM, then n1 square is the LCM. That n1 square after LCM, if you apply square root to that n1 square, it becomes n1. Outside the square root, it becomes n1. So n1 n1 get cancelled. You left with under root within the square root, that is n1 square minus n2 square whole divided by n0. For n0, there is no square root, right? So sin theta naught, this is called as a numerical aperture, because this aperture size, you can see here in the diagram, it looks like an aperture of a lens, but this aperture size, it is derived through mathematical method, hence it is called as numerical aperture. So any light ray which incident within this aperture, it undergoes successive total internal reflection. If the light ray incident outside this angle of limiting angle, that is theta naught, then it is going to enter into the cladding region, that is considered as glass. In that way, the numerical aperture and the angle of acceptance here. The angle of acceptance is any angle which is propagating through this medium. So any light ray which is coming within this acceptance cone, so this takes a form of a cone. The shape of this is like a cone. So any light ray which incident with an acceptance cone, then it undergoes total internal reflection. So this maximum angle theta naught, you can take it as the acceptance angle, and the angle of this cone, that is the acceptance cone, that is the limit. So any light ray which enters within this, that is, if you take theta as the angle of incidence here, then any light ray with an angle less than theta naught, that is the limiting angle, then there is a total internal reflection. If theta I increases, that is equal to or greater than theta naught, then there is no total internal reflection. Okay, so this is the conditions for total internal reflection to happen inside the optical fiber. There are two more parameters which tells about the propagation of light. One is fractional index change and the other one is V number. Fractional index change is the important term, which is the ratio of refractive index difference between the core and cladding to the refractive index of core of an optical fiber. Generally, we represent this fractional index change with the notation delta. So delta is equal to n1 minus n2 by n1. This value of delta, typically it varies from 0.001 to 0.02. And the typical dopants which we select for a silica based glass fiber are titanium, germanium, boron, etc., where the core refractive index can be varied from 1.44 to 1.46. Accordingly, the cladding refractive index also you can change by selecting other dopants. Fractional index change is important because if you take a glass rod, whose refractive index is around 1.5 and the surrounding medium is air medium. So if glass refractive index is more than the air refractive index, hence easily you can think of successive total internal reflections through the glass rod. But experimentally when you try to do it, which is not possible, because the fractional index change between the glass rod and the air medium is very large. Hence, we need to keep the difference between the refractive index of the denser medium and the refractive index of the rarer medium very close to each other. Hence, instead of sending in a air medium, we have a cladding surrounding to the core. The cladding and core refractive indices are very near to each other in such a way that the delta value is between the range, as I said, it is from 0.001 to 0.02. There is one relation between the numerical aperture and the fractional index. That relation is important to solve the numericals. How you arrive at that relation? Here is the relation, that is numerical aperture equal to n1 into under root 2 into delta, where delta is fractional index. To arrive at this equation, let us consider the equation for the fractional index, delta equal to n1 minus n2 by n1. Just cross multiply, you get n1 minus n2 equal to delta into n1. Here delta into n1 is not a change in n1, it is the product between fractional index change value into the core refractive index. Now you take the expression for numerical aperture. Let us consider the surrounding medium is air medium, then n0 becomes 1, then numerical aperture is equal to under root n1 square minus n2 square. Here n1 square minus n2 square is of the form a square minus b square. Therefore you get under root n1 plus n2 into n1 minus n2. Here take this n1 is very close to n2, as I said, you can replace n2 with n1 for the first term, then it becomes 2n1, and for the second term n1 minus n2, from the above equation you can write n1 minus n2 as delta n1. So you get the expression numerical aperture as under root 2n1 square into delta. Here square root, if you apply to n1 square, then square root and square get cancelled, hence n1 it comes out the square root. Hence you get an expression for numerical aperture in terms of fractional index as Na equal to n1 into square root of 2 into delta. The increase in value of delta increases the numerical aperture as per this equation. Also, it enhances the light gathering capacity of the fiber. But delta value can't increase to a very large value because it leads to a dispersion losses. Those dispersion losses we are not going to discuss in this class because the syllabus, beyond the syllabus it is the scope of the syllabus is not connecting to the dispersion losses. The another parameter is called V parameter or V number, which is a normalized frequency parameter, a dimensionless quantity, which determines the number of modes the step index fiber allow to propagate through it. Here, the expression for V, you don't need to derive it, you just remember it is V equal to pi into diameter of the core, d core it's written, into numerical aperture divided by the wavelength of light which is launched through the fiber. Okay, so lambda is the wavelength of light which is launched through the fiber, d core is the diameter of the fiber, Na is the numerical aperture of the fiber, and pi is the constant. So don't get confused the V number with the velocity or the phase velocity or the Abbe number which comes in other chapters. V number in optical fibers is a normalized frequency parameter. Okay, so this V number indicates how many number of waves the light wave can propagate. This derivation is not there, but remember, when the V number is less than or equal to 2.405, the value of V number is less than or equal to 2.405, then that type of fiber is called as single mode fiber, through which only one wave you can send at a time. If V number is greater than 2.405, then that type of fiber able to support more than one wave to propagate. So here is the expression, that is m equal to v square by 2 for the step index fiber. This m indicates the number of modes the given step index fiber supports to propagate. Okay, so m equal to v square by 2. Remember these two equations which helps in solving the numericals. Further, the V number determines the fraction of optical power in a certain mode which is confined to the fiber core. For single mode fibers, that fraction is low for low values of V, that is below 1, and it reaches up to 90% near the single mode cutoff value, that is equal to 2.405. And there is one equation called Marquardt equation for estimating the mode radius of the step index fiber from the V number. Okay, and a low value of V number makes the fiber sensitive to microbends losses and absorption losses in the cladding. Anyway, in the next slides we discuss about the losses. There we come across with different types of losses, in which microbend loss and absorption losses are also one kind. For high values of V, there are other kinds of losses like scattering losses in the core, and also the core at the core cladding interface the scattering losses occurs. For more references, for more information, here are the two websites are given. You can go through with them and you can get more information about the V number and other basics of optical fibers. And in the first reference link you have one calculator also. In this calculator, just by substituting the value of wavelength in nanometers, core refractive index, cladding refractive index, and core radius, you can calculate the numerical aperture and V number associated with this.